Welcome to comp452, and in today's lecture we are going to begin our discussion of MIPS processor that we want to design. We have designed ALU, 32-bit ALU, and we have designed a register file. We know what registers are, and so basically we have all the tools that we need to design a processor in our tool bag or tool chest. So what do we want to design? We want to design a MIPS processor, but we cannot design the complete MIPS processor because we have very limited time. And the other reason is that we just want to learn the basic principles of processor design and fundamental concepts of processor design. Modern processors are actually written in Verilog or VHDL, but that's not our topic of discussion. We do not want to use software tools in this course yet, because that is only possible if we have an associated lab component, and I can actually help you, me and my TAs, because there is some learning curve involved in becoming proficient in Verilog and VHDL. So the first question that we need to ask is which instructions we want our processor to execute. So if you remember, the ALU that we designed, our 32-bit ALU, it can execute these instructions. It can execute AND, it can execute OR, it can execute NAND, NOR. Let's call it NOR. But actually, it can execute NAND as well, but let's just stick to NOR. And yes, of course, it can execute add, and of course it can execute subtract, and actually this should have been number 5. Let me see if I can write it like this. 5. It can execute subtract operation, and it can execute SLT operation, set on less than. So we want our processor to the process that we want to design, it must be able to execute these 6 instructions, and we would also want to our processor to execute load word, which is actually LW, and store word, which is SW instructions. And then we would like to our processor to be able to execute branch. Actually, there are 2 basic types: branch on equal and branch if not equal. So let's execute branch if equal instruction, and branch if equal instruction, and Actually it's called BEQ and jump instruction. We just call it jump instruction. So how many instructions are these? 6 of these: arithmetic, logical, 7, 8, 9, 10. So we want our little MIPS processor to be able to execute these instructions. Okay. All right. Now you can very easily see that what we are not implementing. We are not implementing. Sorry, implementing. We are not implementing. For example, we are not implementing jump and link, and we are not implementing shift left or shift right instructions, and we are not implementing obviously we are not implementing multiply and divide instructions, and obviously we are not implementing any floating point arithmetic. We are not implementing any of these. So let's cross them that we are not doing this stuff. By the way, actually, if you know how to implement these 9 or 10 instructions, you can implement practically any of the other instructions. Actually, we are not implementing load byte instruction, load half word instruction, store byte instruction, store half word instructions. So we will just be restricting our discussion to the implementation of these 6, 7, 8, 9 and 10 instructions. That's it. This is what we are going to do. Okay. So let's briefly talk about these instruction classes. The first 6 instructions that instruction classes R type. Now these R type instructions include add, what we are going to be implementing, subtract, and, or, nor, and SLT. 1, 2, 3, 4, 5 and 6. These are R type instructions. Then there is another category called I type instruction. I type instructions. Actually, all of these R type instructions, they have their I type versions as well. But for now, let's focus our attention on I type instructions include branch if equal, what we want to implement, load word, and store word. These are R type instructions. And third type is J type. J type instructions include jump. Actually, there are other types. There are other instructions as well: jump, register, jump and link. but we will only focus our attention on this one instruction, jump instruction. Okay. Now, basically, what happens when a MIPS processor wants to execute an instruction? Any instruction, it has to be first of all fetched from memory, fetched from instruction memory. Okay. Now, how do you determine the address? Where do you find the address of the instruction to be fetched from memory? We know that address is in program counter, and we call it PC. Now, this PC doesn't mean personal computer, it means program counter. Okay. So this is a register. Program counter is a register. Once we have fetched the instruction from memory, depending upon the type of instruction, we may have to read one or possibly two MIPS registers or two registers from MIPS, register file. Okay, we may have to do that. And once we have read the registers, then we will probably have to perform some sort of operation on them, and then we'll have to store the result into one of the registers. But this is not always the case. For example, when you are performing branch on equal when you are executing branch on equal instruction, then you do not store the result in any register. You do not store the result in any register. You just compare if the two registers are equal, then you jump to some location in you basically jump to some location in you go to some other address in memory. Basically, you alter the flow of execution. You alter the flow of program execution. So, likewise, when you are executing store word instructions, you're not storing the result of some arithmetic operation in some register. Okay, basically what you're doing in store word instruction is that you are storing the value of a register in some memory location. You're storing the value of register in some memory location. Okay, so this means that depending upon the type of instruction, we may have to do some things differently for different instructions. So once we have done that, then we in almost all of instructions except J instruction, except jump instruction, we have to use ALU, the MIPS ALU. We have to use it. We have to use it for R type instructions. It's very obvious, but we also have to use it for branch if equal, load word, and store word instructions. Now I want to clarify this a little bit, how how ALU is used in branch if equal, load word, and store word instructions. Okay, so let's consider the case of branch if equal. Let's say we have T0 comma T1 comma target. Okay, now target is the branch target. So if the value in register T0 and the value in register T1 is equal, if the two values are equal, then we want our execution to jump to this label. Now in assembly language, you know that label refers to an address in memory. Variables are also labels. They are labels in data segment, and the labels in program text segment, they refer to address of an instruction, and they also refer to a function name, because basically a function name is the address of the first executable instruction in that function. Okay, we already know that from assembly language. Now, how is this branch if equal executed? Basically, what happens is that ALU performs a subtraction operation on these two registers. Basically, it subtracts the value of T1 from T0, and if the result comes out to be 0, then it updates the program counter register so that it jumps to this location. Okay, so basically ALU is used in branch if equal instruction. I will be discussing it in much more detail when we implement this instruction, but some of you, I think those of you who studied assembly language in fall 2019, they remember that we did hand assembly of branch if equal instructions, and we saw that although it's an I type instruction, but arithmetic logic unit is used, and basically this I type instruction, okay, by the way, this is one instruction in which there are two different types of ALUs are used. One ALU is the main ALU, and then there is another secondary ALU that calculates the branch target. I think you remember that from our previous discussion, but I will elaborate this in greater detail when we come to that point. Okay, so this is now what happens in case of load word and store word. Okay, let me write it here. Main, actually my handwriting, main ALU is used to perform subtraction operation in case of this BEQ. Okay, in these two cases, main ALU is used to calculate a memory address. Okay, so once again, so ALU is used here, and of course it's used in all these 6 instructions. Okay, so only J instruction is the only instruction which does not use the main ALU of the MIPS processor. Okay. Good. So it means that we if we want to construct a general block level diagram of our MIPS processor, a very general block level diagram which will have many details missing from it, then we can say that once program counter is used to fetch an instruction from instruction memory, its value has to be incremented by 4, and then once again when branch is taken, then we have to calculate the branch target as well. Okay, so let me by the way, you remember that every MIPS instruction is 4 bytes long, no more no less. So it means that if you know the address of one instruction in memory, you know the address of every instruction in memory. You know the addresses of all previous and all following instructions. Okay, that's because every instruction is 4 bytes long. And another important thing is that all instructions are located at addresses divisible by 4. And this means that all the addresses, all addresses in which the last 2 bits are 0, they are divisible by 4. Okay, you already know that. So basically, what do we have? What do we need? First block that we need is program counter register. Then we will need instruction memory. Then we will need the register file, which will have 32 MIPS registers. This is actually dual read port register file, the one that we designed in Appendix B. Then we need ALU. Then we need data memory, and in addition we will need a couple of adders. So let me see if I can uh, pause this lecture for a few seconds and quickly download the figures, the PDF figures from my Google Drive. So I'm going to pause this lecture for a couple of minutes. So there we go. All right. So I'm back. I've downloaded the file, the two PDF files, and now I am going to show you a very basic high level diagram of what we are going to do, and then I will also point out the deficiencies in that figure, and then I will show you a better figure, but it will also be missing a lot of details that we are going to fill in step by step in the next lecture. Hopefully in the next lecture we will complete it. So basically the figure that I'm going to show you is called a high level block diagram of data path. Now data path is, what is data path? Let me write it here. Data path is the set of lines on which data travels. Okay, so what else, what other paths do we have in a processor? It's called control path. Control path is the set of lines on which control signals pass. Control signals travel. TR for travel. I've run out of page. Okay, so you understand now that we are initially going to design data path, and then once we have designed the data path, then we will work on control path. So data path is more important because data path does the actual processing of information and control path only facilitates that processing. Okay, so now let me show you page actions. I want to insert PDF and I want to bring it from internal storage, download, okay. There we go. Let's make it. Oh, good. Now this is what you want to do. Look, let me use a different color. I have lots of color available. Let's use this color. Actually, this is the color of Prime Minister Modi and India, saffron. So this is our instruction memory. This is our register file, our data memory. This is our main ALU, and this is our program counter. Now let's see what's happening here is, let me use blue color now. Program counter register, it sends the address of the next instruction to be fetched to instruction memory. instruction memory, and instruction memory produces the instruction code at that address, instruction code at this address. It brings it to its output port. Okay, from here the instruction parts of instruction, they go to register file, and part of the instruction goes to this adder. We'll talk about this adder in detail a little later, probably in the next lecture. Okay, and then you see these two register values. This is register 1. By the way, if you since you know the assembly language, this is RS register and this is RT register. Okay, and this is basically the value of RS register. This is the value of RT register. Okay, RS register number is probably here and here. We will have a much more detailed diagram. For now, it's just a high level overview, nothing more than that. Okay, and for R type instructions, this input of ALU as well as this input of ALU, they both come from register file. Okay, and by the way, you can see here that this program counter is also going into this adder where 4 is added to it. Now this is PC plus 4. This PC plus 4 is the address of the next instruction in this instruction memory. Okay, and then again you have another adder here. This adder actually produces branch target. How it does that, we'll take a detailed look in the coming 1 or 2 lectures. And you know, this is doing either addition, subtraction, and or not and or nor and SLT operations. And this is the address input of the this is the address port of data memory, and this is where the data is. This is the data port, input data port of data memory. This is output data port of data memory. So if you want, now this line brings data that store word wants to store in memory, and this line produces the data needed by load word instruction. Store word instruction, and load word instruction. So store word instruction deals with basically these are 32 lines. So these 32 lines carry the data that store word wants to store in memory, and these are again 32 lines. They bring the data that load word wants to load and store in the register file in one of the registers. Okay, so far so good, but this instruction, this figure, it does not show any control signals, and also it does not explain one more thing, and I'm actually going to now use the red color to point out the serious deficiencies in this figure. Okay, now first let's take a look at, data is coming from here and data is also coming from here. So this is a point which is receiving data from two sources, and then that data is moving in this direction and going to the register file. Okay, so we have a problem here. Again, look, some value is coming from here and some value is coming from here, and then it is going in the program counter register, program counter, this program counter. Okay, all right, then again, so it means that we have a problem here. There's a problem here. Let's write a question mark. And then again we have some data coming from this side and some coming from here. So again, this is where we have a problem. So all of these circles with question marks are points. These circles are around points where two data sources are kind of merging. Two data sources are sort of merging. But of course we know that this cannot happen. So whenever we have two sources of data or two inputs and only one output, then it means that we have a multiplexer there. So this is, now I'm going to use a green signal, a green color. This is here a mux is needed. Again, here mux needed, mux needed, and again here a mux is needed, multiplexer, mux needed. Now if we are going to have these three muxes here, then these muxes will have select lines as well, right? And those select lines, if you remember, we draw them in blue color because they're control signals. Our data path is drawn in black color in your textbook, and control signals are drawn in blue color. Okay, so see, we need three muxes here, and those three muxes, with associated control signals or select lines, control or select lines are needed. Now I am going to ask you a question. Let's actually label them. Let's call this, how do we number them? Let's call this number 1, first mux. Let's call this number 2 mux, and this is our number 3 mux. Now what will be the size of the number 1 mux? Let's go back to black color. Size of mux 1. What will be the size? It will be, how many data sources do we have here? We have 2 data sources. Okay, so we need a 2 to 1 mux 32-bit wide. Why 32-bit wide? Because both inputs of our ALU are going to be 32-bit numbers. Okay, now let's come here and let's see what would be the size of this mux number 2. Again, we have 2 sources, 2 inputs. One is coming directly from ALU and the other one is coming from the output port of data memory, output data port of the data memory. So we have, this is 32-bit line, as we have written here, and this is also 32-bit signal, 32-bit number. So we have two 32-bit numbers and only one of them is going to go to this data input. So size of mux2. What will be the size of mux2? Two data sources, 2 to 1 mux, and again 32-bit wide. 32-bit wide. Okay, good. Let's come here. Again, mux3 is size of mux3, same 2 to 1 mux, 32-bit wide. So basically we are going to have three select lines. Three select lines, because each mux is going to have one select line because it's a 2 to 1 mux. Only the size is big, it's 32-bit wide mux, but it's only 2 to 1 mux. Okay, so three select lines. These we are going to call them control lines. Control lines or control signals. So we will look at these control signals very soon. Okay, so I think now it's time that I show you the next figure. Oh, I went way too far. Okay, there we go. So this is our figure. Okay, so you see, if I look at the numbering we did in the previous figure, this is 1, 2, and 3. Okay, so this is our mux1, this is mux2, and this is our mux3. You see, this has one select line, this has one select line, and this has one select line. All three of them have one select line. Okay, now in addition we have a few more signals. Look, this is reg write, this is a control line or control signal. If this signal is asserted, it means we want to write value in some register. Okay, remember this zero output of ALU? This output is asserted only when the last operation performed by ALU produced a zero result. Now this is mem write and mem read control signals. They are associated with the data memory. Okay, so all of these and then of course remember this is ALU operation is a 4-bit control signal, 4-line control signal. You remember our ALU has 4 control lines, and those 4 control lines are controlled by this controller. Actually we will see that we will not have one controller, but we will have 2 controllers, but we will talk about that in the incoming lectures. Okay, so once again this figure has a lot of missing details. A lot of details are still missing, and that's what we those details are what we are going to fill in by starting with a very basic data path. And by the way, initially our initial data path will not have any blue lines in it. It will just have black lines, and once we have completed the data path, then we will start working on the control path or control. Actually, you know, it's also called data plane and control plane. When I was working at my company in abroad, we used to hear a lot of these data plane and control plane talk. Uh, Basically, data plane was the path in which the data traveled through routers and switches, and control plane was the collection of signals, or collection of basically signals or paths or wires on the motherboard, which controlled the operation of various uh, subsystems that were processing network data. Anyway, so right now you can see that there are 1, 2, 3, 4, 5, 6, 7. Actually, these are not 7. These are more than 7. These are 8. Now this is input of control. This is and this, by the way, the input of this control circuit, it also comes partially from the instruction. So what I want you to do is, I want you to look at this figure and just try to construct a picture in your mind. What are these black and white lines actually doing? For example, I would want you to think about this input. Actually, let me use a different color. How about using purple color? I want you to think about this signal, and I want you to think about this signal, this AND gate, this signal. You know that this is zero signal coming from ALU. And I want you to think about this signal. There's something missing here. There's something missing here, but I want you to think about it. There is a combinational circuit that we will insert here at this point, but I want you to think about it. And also I want you to read section 4.1 and 4.2 of your textbook, Patterson and Hennessy. Okay, so this is where I am going to stop. And oh, what's happening? And I'm going to upload this lecture. Oh, I'm sorry, did not intend to do that. So now I'm going to stop. All right, there we go.